Hi, thank you very much, and nice to see everybody. Thank you guys for a wonderful day so far. Very much appreciate everyone's efforts. So it's an honor to be here with you today, and I'd like to share with you kind of an overview of my research program and kind of the scope of the trajectory of how it's kind of moved and grooved through the years, and kind of summarize kind of what the title is alluding to, this journey scientifically from memory to different mindsets. That is, we're going to talk about basically pre-stimulus brain activity that kind of is a state supporting cognition, and then how we've sort of explored that using applied settings at NASA, looking at astronauts in simulated space environments and things like that. So that's kind of the scope. It's a difficult talk for me to give because it's a lot of stuff that's really different that I'm going to try to weave together into a cohesive story. So bear with me if you may. See if I can turn this forward.
This is test number 1.
Yeah. Is this?
Is it on?
That's okay. I will use the mouse.
There's an
There you
on.
This works.
Yeah.
The other.
It's on.
Okay. Well. Okay. There we go. So first, just I kind of have a bold title for the talk, right? Memory, mindsets, and a mission to Mars. So what the heck? How does this all connect? Our psychology department not always at the forefront of our minds of how our brains are going to get us to Mars, and what's the relationship. So why is psychology in Mars? Well, this is just sort of a general overview. So this is a picture I took with my cell phone from the wall at a place called Rocket Park, which at Johnson Space Center is where they house the Saturn V rocket from that would have been Apollo 18. And so it just kind of shows NASA's big picture from Earth. So we're here at that yellow spot there. Where we want to be is here on Mars, right? And we'd also kind of like to do this last part of coming home, right? So what that means is it's a really long trip. It's about 3 years or so. And the toughest part is actually surviving each other in a small capsule about the size of a camper. So imagine taking 3 or 4 colleagues from work and being in a camper for 3 years together. Just imagine like your best faculty meeting ever. And it just doesn't stop for 3 years. That's what we're dealing with. And at a serious level, right, we need to understand what's going to happen to humans in isolation, confinement, the psychological sides of this, so that we can do that challenge of surviving each other to not just get here, but we want to survive each other and come home happy because we need to get along. Team dynamics, cognition is going to play a role in that. And so when we go to Mars, our rockets are going to work, but the lingering question is whether or not our people will. Are we going to work together? So our rocketry, our engineering is already on the red planet. We need to make sure that we need to understand ourselves next before we really embark on that next great step throughout the universe. Because the errors of cognition can be catastrophic. So, if you haven't slept, or if you have a attention failure, a memory failure, that can happen, on the road, driving around, right? That can be catastrophic in space. So there's a prime interest in that. And so I'll try to connect those dots a little bit. And that's kind of where we're headed. So I'll start with the story basically about how I kind of got there in my research program through beginning studying memory. So brief outline that I'll kind of talk about is summarizing my research on the cognitive neuroscience of memory. I'll look at some clinical research studies that we've done looking at amnesia patients, as well as some normative studies using EEG in healthy, normal populations, and how that's connected to studying brain states, which was an accidental discovery that we came about, and how that's connecting with this broader mission, studying cognition, and what we call analog studies, which is an analogy for space. So an analog is what they call them. And we'll talk about a couple different missions that we've had the privilege of being a part and kind of wrap up looking at some future directions. So I want to introduce you first to the memory part of the talk, the core part of my research program, and introduce you to Juno. So this is Juno. She's a 6-year-old greyhound that we rescued from Greyhound Rescue in Dallas when she was just a puppy. And she's spoiled rotten. She's near and dear to our heart. This picture is a few years old. But she really likes to play. She likes trail running, swimming, all that kind of good stuff. She likes to travel. She loves the open road. When she was little, she really liked to ride shotgun. You can see she grew up a little bit there in the middle. And now she's sort of a full-grown doggy, and she prefers to drive. So what I want to ask you, though, now is to imagine if you only had memory for those sentences instead of the rich context of the imagery that went along with that episode of that last experience you had, engaging with that information. So a kind of a black and white version of your world, right? So if all you could do is just remember these semantic pieces of information, sure, it's better than being fully amnestic, but that's not really what we would normally consider a rich and fulfilled life if you can't recall that rich contextual information of the episodes of your birthdays, your weddings, your anniversaries, big events in life. And so that's kind of what we look at the core level of my research program is how do we remember and retrieve that rich episodic information from our past? And so the central questions that we kind of look at is how does that operate, but also what happens when it fails? So we look at that in cases of amnesia patients, but also cases of normal forgetfulness that I think we all have at times. And we also address some ways and strategies that we can look at for possibly improving that memory, and we'll kind of look at that a little bit, and help prevent our decline from our normal memory failures in aging. And that kind of led to these questions about if there's brain states that can be associated with this enhanced cognition. So that's kind of the scope of the research that I'll cover at a big level today. And I'll start by just introducing some of the main measures that I use because I'll show data throughout the conversation today, and they're going to come from multiple modalities. So we do some basic cognitive and behavioral tests of memory, ask people to perform a basic memory task on a computer screen. You'll measure that in reaction times, accuracy. But we'll also look at that in neuropsychological patients. People who've had brain damage, amnesia for various different kinds of reasons. Particularly in this research, we've looked at patients who've had selective hippocampal damage. That's come from mild hypoxic events, that is about 3 to 5 minutes without oxygen. It tends to leave a selective lesion on the CA1 area of the hippocampus. And a large chunk of the work that we did also then added electrophysiological measures from EEG and looking at that both in healthy normal populations as well as those that are clinically amnestic. When we look at some of that data, we can see that you can get different electrical readouts from different areas of the scalp. It's non-invasive. And we can plot that either as an event-related potential, which looks like kind of an electrical squiggle that bumps up and down. So that's what you'll see me refer to as ERPs, which is an event-related potential. Or we can also plot it as a spectrogram, which is a way to characterize and quantify the oscillations, so basically the waviness of the data. So you'll see some of that data kind of interspersed. We'll have time always usually on the x-axis, and the y-axis in the spectrograms is going to be frequency in microvolts when we look at the ERPs, sort of that electrical activity. We'll also see data plotted as topography maps. So what this is you could have essentially a subtraction of two different electrical conditions, or I should say electrical waves of different memory conditions, say remembering and forgetting. You subtract that, what we call subtraction analysis, and that resulting pattern of activity is what we link to that being ascribed to that cognitive process, that memory of that particular instance. And when we see this data through the conversation, this is a bird's eye view looking down on the scalp. So you have a nose, a left ear, and a right ear. And as you might imagine, you might be familiar with looking at images of MRI activity too. So we've done some neuroimaging results that I'll talk about, where you looked at fMRI activation, particularly during the learning phase of memory, when people are studying information and the scanner can produce these nice three-dimensional representations of blood flow in the brain. And we'll look at that in applied elements of brain states and talk about some other approaches we use to intervene and improve memory when we can, namely entrainment, which I'll talk a little bit about, as well as things in the future that we're looking towards, like transcranial direct current stimulation. So, without further ado, two big things that we kind of know about memory in the field, two pillars. If we don't know anything else, there's kind of these two things that we're pretty sure we know, which is one, that memory depends, particularly long-term memory, depends critically upon the medial temporal lobes, particularly this area called the hippocampus, kind of wraps around in the C shape. You can look at it at different sort of angles depending on how you slice the brain. And that's a big core of the research that I'll kind of show a little bit of our work towards. And a second big thing in the field that we kind of focus on is this idea that memory is based upon stimulus-response relationships. So think about your standard Psych 101 Pavlovian conditioning. There's a bell and there's a salivating dog. So stimulus and a response. So that kind of has formed this sort of foundation for a lot of the science and approaches that we've done about the last 100 years or so since that seminal finding. So I'm going to look at data in those two big sort of picture frameworks. First, looking at long-term memory and its dependence on the medial temporal lobe. So that sort of hallmark finding in the field has come about famously since 1957 when we had famous amnestic patient HM, who everyone probably remembers, no pun intended, that he had a bilateral medial temporal lobectomy to try to address intractable epilepsy. So they cut out both of his medial temporal lobes when he was about that age, and he lived the rest of his life to 2008 without the ability to form new long-term memory. But critically, what he showed us was that he could retain the ability to do non-conscious memory, so the hippocampus wasn't necessary for implicit memory. And it gave us this canonical sort of memory tree where we had long-term memory that was conscious and declarative, and that was non-conscious and implicit. And I'll talk specifically about this kind of memory called episodic memory that we introduced a little bit later, or earlier I should say, and raise the question about if we can add some new branches to this sort of prominent tree. Namely, this process of recollection and familiarity. There's been a lot of debate in the field over the last 20, 30 years. Are these different cognitive and processes, and are they served by different neural structures in the medial temporal lobe? So recollection you can think of as that really clear, crisp retrieval of information with the context, the details, what happened, when, by whom, as opposed to that sense of someone seems so familiar, but where do I know them from? Right? So memory works, right? If they seem familiar, I feel like we've had a prior experience together, but it also doesn't complete all those extra pattern information. So these are both a way to recognize information from our prior episodes, but there had been a lot of debate about whether they're separable trees, or branches in that tree. And so I'll present a little bit of data that we first explored, asking whether or not recollection requires a hippocampus, and if so, which of these processes are impaired then in patients, clinical patients, who have damage to that hippocampal area. So, in addressing those questions, one of the tools we used was electrophysiology. And the reason for that was because these event-related potentials, it turns out there's a very rich literature that already existed in the field identifying that there's some really clear, what you can think of as sort of biomarkers or electrophysiological signatures of each of these distinct processes for recollection on one hand and familiarity on the other. And so I'm going to start referring to them a little bit interchangeably for the rest of the talk today as what we'll call the FN400, which basically stands for a frontal negative going wave that happens at about 400 milliseconds. So this negative deflection that separates for conditions that are both familiar versus non-familiar or new. And that really turns out to be quite distinct electrophysiologically from what we see happening at the left parietal cortex instead, which happens a little bit later in time from about 600 to 800 or 600 to 900 milliseconds. So we abbreviate that as an LPC or a late parietal component. And you can see that they have different, couple key things. They have difference in timing and difference in topography. So they happen in different times, so an early effect versus a late effect. And they also have a frontal effect versus a parietal effect. And so it gives us some really good tools to ask those questions about what's impaired in hippocampal amnesia. And that's kind of where we began that journey. And so what we did, this is actually some of my dissertation work at UC Davis. We worked with the Northern California VA system there to identify some patients who had some clinical amnesia disorders by virtue of these hippocampal damages. And we asked them to study a list of words, one at a time, about 200 words, and then later on we tested them on their memory for that words. But we didn't just ask them yes or no. We gave them this much more subtle task of rating their memory on a confidence scale. Now, the reason that's important is because it's going to give us some tools scientifically to quantifiably assess that memory. So they might respond 5 if they're absolutely sure they know they saw that word during the study period, or 1 if they say, no, I'm definitely sure I've never seen this is a new word. And some levels in the middle of, oh yeah, I think that seems pretty familiar, but I'm not entirely sure. So it gives us a pretty sensitive tool to capture those fuzzy cognitive processes. When we did that, we could see that our healthy controls, we had 6 healthy controls. They have a very nice hippocampus bilaterally, but we can see pretty clearly that sort of big hole there in the hippocampus of a representative patient. So when we tested their memory, first thing that we looked at was behavior. So what we're looking at here on behavior is, this is their percentage of idle memory correct. That is hits minus false alarms. And normal controls are performing at about 55%, which is pretty good. There was a significant drop in memory performance in the patients. That is, they were clinically impaired compared to controls. But what's also really interesting is they were not at chance. They were not down here. So they both performed above chance, just not good enough as everyone else. Which raised the question, are they impaired in recollection or familiarity, or a combination of both? And that big question fed into larger debates in the cognitive literature. And we addressed that with these ERPs, and what it showed was that when we looked at the FN400, this frontal negative domain signal about 400, our controls had this nice mid-frontal effect that we introduced earlier. And just like you would expect if it was not impaired, there's the exact same signal in our patients, in that early effect for familiarity. But what we found is that we had this traditional, really prominent left parietal effect. One thing you might even pay attention to is that the magnitude of the scale is very large. It's a 3 microvolt for this difference wave. But the patients are completely abolished and impaired, and the scale even changes for the patients. So basically, they were completely gone in that recollective process. So we've used this really sensitive tool of physiology to answer this very subtle question of cognition, and particularly applied that to these clinical conditions of hippocampal amnesia. These are the ERPs that correspond to that. So these are the control subjects. So that's this wave here. This big red splotch is subtracting these 2 signals of our high confidence and low confidence hits. So we're subtracting 5 and 4s. And you can see again, this big difference is evident here, and our patients are just completely washed out. So if you guys see down there, that's that bottom right-hand little spot here, and there's just absolutely no difference. What you're going to look for in some of these slides is any action or difference between the 2 lines. You can see here it's just completely washed out. So it gave some pretty strong evidence for us towards addressing that question of, are there these 2 extra branches that we can now add to our framework of understanding long-term memory for episodic processes? And it seems like there was, particularly in this declarative memory tree. So that was pretty exciting, and they let me graduate, and that was cool. I was very grateful. Because I know some of you guys do a lot of clinical work, and this stuff is hard. So I had a fancy long title during the dissertation defense, very scientific sounding thing, and then it faded out, and I replaced it with, or why it took me 5 years to test 3 people. Because it's hard. And we got to be very careful. And we did a lot of other studies along the way there. And I'll share a little bit about that too. And so I'll pivot a little bit now to draw upon that data that we collected for conscious memory and start to look at this question of non-conscious memory too. Because it's an area that's long been neglected about the hippocampus. We never thought that the hippocampus would be involved in implicit memory, because when it was gone in patient HM, he never had any problems. But, I should say, and that's become textbook dogma. So this is the Principles of Neuroscience. It's basically the Bible of neuroscience. It's about this thick. Graduate students either love it or hate it. And it was written by this guy, Eric Kandel, who he's accepting the Nobel Prize there, I think, in about the year 2000 or so, for his work studying non-conscious memory in sea snails, it turns out. And so it's in all these textbooks. It says implicit memory does not depend on the medial temporal lobe structure. And something I want to suggest to you is this idea that we've been working with in the lab for quite some years, which is the suggestion of, what if we've been looking at reality that is a 3-dimensional picture, but we're only using 2-dimensional lens? So we were wondering what the role the hippocampus might actually play in implicit memory. Perhaps it plays a more prominent role than we might have otherwise thought. And so most people haven't looked at that. And in fact, you probably couldn't get funding for it, because why would someone fund doing EEG of implicit memory in hippocampal patients when all the textbooks say it's going to be fine? Right? Is that good use of your tax dollars to have somebody do that? It was kind of the scientific thought at the time. But I didn't have to write a grant for that. I already had the data from the explicit task. But here's the question now, kind of a conundrum. How do you capture non-conscious memory activity when subjects were doing a conscious memory task? And the answer is the same way that porcupines mate, very carefully. So, using EEG, we can be very creative and use what other people have done in the basic science literature. And what they do is you can compare the brainwaves, these event-related potentials, for times when people say they don't remember, but they're wrong. Happens to all of us, right? We forget stuff. Have you seen this before? Nope. Okay? So we call that a miss. Because you don't have any conscious experience of that memory, but we know it happened. We compare that to brain activity when they're right about not remembering. We call that a correct rejection. They're correctly rejecting the lure. So, what are the variables that are held constant here? It's their conscious experience, which is nil, by the way. Both situations, they're saying identically, I do not have a conscious representation of this memory. But if we look at the physiology, this biological activity is differing. So you can think of it, the mind is forgetting what the brain has remembered. So another way, the brain is remembering what the mind has forgotten. Okay, so that's what we're going to look. This is going to be our tool. And previous research from 98 and a handful of other studies has found that this is the sort of this posterior parietal activity shows this difference at about 400 to 600 milliseconds. And so it gives us a hypothesis that we can look for to see if that's affected in hippocampal amnesia, because we already have the data. And that's indeed what we did. And so we're going to look for that difference, like I said, about that time. Remember, the timing is important. We're going to look for about 400 to 600 milliseconds, stay consistent with the hypotheses generated from the literature. And this physiology is really useful. And we're going to look for it in this sort of posterior area. You guys can see my little pointer down there. And so when we looked in our hippocampal patients for that, we found something that was kind of shocking for us, very surprising. So this is our healthy control here. And it looks exactly the way that last slide's data looked. Big, huge effect in the posterior area. Big difference of the brain remembering what the mind has forgotten. However, when we looked at our patients, it not only was it completely gone, it actually reversed the opposite polarity. It was still significant in the opposite direction. This was really shocking to us because the hypothesis here was actually that both would be the same. So I kind of actually didn't believe it for a while. I scratched my head because I wasn't even trying to find it. I was actually trying to show that they were the same to rule out an alternative for that earlier finding. Did a bunch of control analyses. There's like 7 other figures in that paper that are all just control analyses ruling out other options. But what it kind of arrived to was this core idea that we had a reliable condition by group interaction. These are each of the subjects, so there's no outliers driving. This is pretty powerful. And it kind of gave us this idea that the hippocampal patients were impaired in this measure of implicit memory. And it seemed then that there's this form of non-conscious memory that actually does depend on the medial temporal lobe, contrary to all of our sort of prominent textbook models that had existed up to that point, and suggesting that maybe our conscious and non-conscious memory systems were operating on the same structures of the brain, but perhaps being processed in different ways, because the physiology reversed course. And so that kind of questions that canonical distinction we've seen in some of the prominent textbooks, and to my everlasting delight, it's actually been added to a couple new textbooks that have come out in the time since. So I don't get a chance to tell people that much but I definitely can get my geek on a little bit about that. It was pretty cool to see. So we're definitely very proud of that finding. And so that's kind of summarizes some of the big clinical works that we've done. Now, I'll kind of pivot now because I was pretty excited about that. And one of the reasons I said I don't get to tell people about that a lot in the book is because I'm always scared about being wrong about it. And that's why I did like a ton of control analyses and all that. And it kind of got me thinking, and it's become this new direction that we're doing in the laboratory where we're starting to look at metacognition. So what if we're wrong? So it turns out humans have a really, really good ability to overestimate ourselves. Nobody's better at this than professors, right? Because there's research that shows if you ask professors to rate how good of a teacher they are, everyone says they're above average. Statistically impossible, but it's not an uncommon human phenomenon. So it goes back to Confucius has addressed it. Aristotle has been puzzled by it. Shakespeare said, "The fool doth think he is wise, but the wise man knows himself to be a fool." And so what we're talking about here is metacognition. How do you know what you know? And are you right about what you think you know? Right? So a little flare of philosophy, but we're going to turn into sort of social cognitive neuroscience. And this is, in the field of social psychology, people have looked at this effect called the Dunning-Kruger Effect. And what that is, it refers to researchers David Dunning at Cornell and his graduate student at the time, Kruger, who's now a professor, I think, in the business department at NYU. But they studied this effect, and they found this really famous finding. So what you have here is actual performance plotted by perceived performance. So you have a little bit difference here where this is actual performance. Some people underestimated how good they thought they did. Now, many of you guys might know that some of your students like this. You ask them how you do after the test, they're like, I don't know, I didn't, it was hard. They ended up doing really well. But most of your students, and indeed most of us at times, right, how do we think we do? Oh, we did fine, but our actual performance is really much lower than we thought we had done. It's sort of a very pervasive phenomena. They found it generalized to lots of things: logic tests, math tests, SAT tests, LSAT tests, driving competence, how well you are at card games, and of course, professors' teaching abilities. So our question was, what are the neural and cognitive mechanisms supporting this? And when I looked, I couldn't find any. It was just kind of a whim that I started looking on PubMed for this. And couldn't find any. And so I kind of had an entrepreneurial spirit about it and said, well, somebody should do this. And I hate saying that because then I'm like, well, somebody ought to do it. I guess it ought to be me. And so we embarked on this new exploration where we had to ask, how can we study it? And this was a difficult thing because if we're going to study it the way that we do in our laboratory for ERPs or any kind of brain measures, or even reaction time measures, you need many measurements per subject to average. And these studies always only ask once at the end of a task, how did you do? And they say, oh, I did okay, I didn't do so good. So one measurement is not going to get it done. What we did is we drew upon the literature that I've kind of introduced to you a little bit about our ERPs and added to our normal experiment where we asked, how are you doing on a memory task? If you remember this, 1 to 5, old to new. In every 10 trials, we now added an estimate for Dunning-Kruger. So they were supposed to estimate what percentage they're performing. They're estimating their performances relative to others on this task. Are you basically getting an A, a B, a C, a D, or an F? Right? Are you in the 90th percentile, the 80th percentile, et cetera, et cetera? And because we had about 300 trials at test, we did this about every 10 trials. We got about 30 trials per subject, which was really good for signal-to-noise ratio. And so we kind of created this new innovative sort of paradigm in order to assess this because it can give us questions, give us data to answer some hypotheses and predictions we can make. So using what we know about this task, we can assess, is there a cognitive process that might be supporting this experience? Familiarity or recollection would be indicated by an FM400 or an LPC, respectively. Now, the idea that we thought about memory wasn't just because when you have a hammer, everything looks like a nail. We're memory researchers. That's my hammer, and so everything looks like a memory problem. But if you think about how this works, you have to remember, in order to assess how are you doing, you have to have some sort of an anchor point to reflect back on. You have to remember how you did. And so we thought that there might be some memory component to that. Dunning-Kruger's account, when they reported in the literature, all they could come up with at the time was something they called reach-around knowledge, which was you had a little bit of knowledge which allowed you to reach around to your conclusion and make an assumption about your performance. But that seems to me like a lot like familiarity. You got a little bit of information and it allows you to make a judgment. So that's why we kind of thought that these could be a good way to investigate this question. So when we did that, the first thing we found was that we were able to replicate the effect, which gave us the ability to sigh a big breath of air, because at least we had something to look at, right? Because there was no reason this would have worked. We invented a new paradigm, basically. But this is our data, and you might notice it looks very, very similar. So we have actual percentage, essentially, in quartiles versus their estimated. And we have our standard Dunning-Kruger effect. We quantified this, and it was reliably significant. So it allows us to say a couple firsts that we did. We were able to basically extend the Dunning-Kruger effect to episodic memory and its respective paradigms, and also be able to do it in a way where we were able to capture multiple measures, both for physiology as well as to look at behavioral reaction times, which to date neither literatures have been able to do. A small note as we go through the data. We collected data from 62 people, I think. A couple of those weren't available for technical reasons or poor performance, so we had a sample of 56. And when we sliced and diced our groups into those who overestimated or underestimated, and a small group of people who were basically accurate, our sample sizes were 38, 10, and 8, respectively. So just a little bit of science there as we move through here. The next thing we did was look at behavioral measures, reaction times. And this was really spearheaded by a graduate student in the lab, Alana Muller, who took this sort of up and championed the behavioral case. I was always thinking about the brain measures, but she really thought that there was something there. And when she did look, we found a really cool finding. We basically found a crossover pattern, crossover interaction. So here's the thing. When you ask people to rate, are you doing good or bad or however, we looked at the two polar ends of that scale. Sometimes I'm saying, I'm doing great or I'm doing terrible. Now, it turns out our overestimators, our braggadocios, right, which we're all in at one day or another in life, right? We overestimate our abilities. They were fastest. Oh, sorry, wrong color. Overestimators, blue. They were faster to say that they were doing great, but they were slower to judge themselves as doing poorly. On the other hand, our underestimators, our sort of humble heroes, they were slower to say they're doing great. They were faster to say they're doing terrible. So there's a crossover pattern there with accuracy. Both groups are slower to say the right answer, but faster to say the wrong one. So it's like striking to me. My graduate student figured that out. She looked at that, she brought it to me, and I was like, wow. Can you not graduate, please? Like, stay around a couple more years. This is great. We need you to stick around. Unfortunately, Alana did really, really well. As you'll see, she got some other great data. She's now in a PhD program at the University of Arizona. She's doing a great job. But when we looked at the physiology then, we're going to look at two things to ask two questions. One, what is different in people who over and underestimate themselves, right? It's kind of that core question, at least I was interested in. It's just like, what's happening here? Why are people giving these fundamentally different psychological experiences? And so to do that, what we did is we looked at all of those 1 to 5 Dunning-Kruger judgments collapsed together. And then we separated those based on what group membership they had. Were they the overestimators or the underestimators? And this is what we found. Okay, so this is the ERP and this is the difference wave between them. We had this big prominent mid-frontal difference between the overestimators in red and the underestimators in blue. That was reliably significant. And to us, it sure looked like that there was familiarity-based differences in this FN400. Early, at exactly that time point, 406, and mid-frontal as well. We're pretty excited about that because, for one, there was no reason to think that our null hypothesis would not be correct. So just to see anything, we were pretty excited because it was kind of a shot in the dark to attempt this study. So we were excited, and we kept exploring. The next question we asked was, are the people remembering differently? Is there a reason that they're having this different metacognitive experience? And it looked like there actually was. So what we're looking at here, these two ERPs each represent memory effects for the different groups. That is, the blue and the black ERPs each represent a difference wave between our memory categories of the hits versus correct rejections, which is what we usually use to plot our ERP effects. So what that means is this is a big difference. Blue is different than essentially 0. This is our 0 difference. Hits minus correct rejections in our underestimators was huge. So the underestimators had a huge late parietal effect that was not evident at all in our overestimators. So that was also really exciting for us. Because it was like, wow, that did not have to be true. We were pretty interested. So it looks like recollection is influencing how people are making these judgments. They're actually remembering differently. And as they're remembering differently, they are then going on to metacognitively assess themselves in fundamentally different ways. We're pretty excited about that too. I'm excited, by the way, to share this with you. This is the first time I've shared this data outside of like a conference poster. It's submitted right now. It's under review. It's available at bioRxiv. But I'm really excited also to talk with you guys offline and hear what you guys think about it. Maybe we're missing something we also want to get better at. So as we got excited about that, we looked in a little bit more detail and asked if there's a systematic relationship across subject, and it turned out there was. I'm not going to spend a ton of time on this because I want to transition to the next sort of part of the talk, but the big idea is we looked at that LPC magnitude, that recollection signal. It was reliably predictive in a positive way, first, of how many memory hits the subject had. So the bigger the LPC, the bigger your memory store. Next, it was also negatively predictive of your reaction time for those recollection experiences. That is, the bigger your recollection physiology, the faster you responded in that instance. So again, linking this very strongly with recollection processing. And then what was really interesting is we pulled out the two groups separate, and it was our underestimators. So this was this open circle that was reliably predictive in a negative way for their average performance estimates. So the bigger your recollection effect, the lower you thought you were doing at a subject-wise level. So now we're actually finding a systematic relationship between this physiological correlate of a cognitive process and their metacognitive judgments of some of their own self-reflection, which was like staggering to me. I was like, I can't believe we got this all in one data set. But it's tested. Alana spent several years getting 60 people. It's a huge sample size in ERPs. And she did this once with a sample size of 40, and we realized that our subject pool was responding randomly for her afterwards. So she had to rerun the study. It took her basically another year. So this is a huge testament to Alana. We really dialed this in. We were really committed to this, and she found some really cool effects because of it. So looked like the bigger the LPC there was, the more memory there was, and that the more recollection they had led people to become a more humble estimator, which kind of makes sense. You have a little bit more constraints to guide your estimates. So in summary, sort of the finding, we found several of these crossover patterns. So we found that crossover in behavior. This is a summary figure of all the same information. I just put it together on the same slide. So you have the familiarity effect and the recollection effect. And you still have that crossover pattern across groups. So revealing that core role that memory is contributing to these metacognitive judgments of illusory superiority. And so the question kind of, you can think of it as summarized, how did the best performers stay humble and avoid that overconfidence illusion? Well, they avoided using familiarity. And they made specific reliance on that clear, distinct recollective process instead. So familiarity is kind of a heuristic that kind of guides us to use guessing and stuff like that. Whereas the recollection exhibited that more humble, metacognitive self-awareness. And so that's kind of what was special about these underestimators, these sort of humble heroes. They didn't, by not having that familiarity, it led them to not have the errors of overconfidence. And like vice versa, the people who did not recollect the details, that made them think that they knew it all, essentially, colloquially speaking. So, if there's a simple summary, whether you recollect your details or not, stay humble. Because if you do recollect the details, you're already more likely to actually give a more humble assessment. And if you can't recollect the details, that should be a warning sign. Definitely stay humble, because you might be about to make some pretty overconfident illusions. So anyways, we're pretty excited about that. At the end of the day, we hope that it's something that doesn't provide answers to the field, but opens the door for new explorations to dial in. Can we covary that with gene assays, with personality inventories? There's a lot of work to actually explore what's happening here. But now we've created a paradigm that other people can take with, and certainly we hope to continue to run with. And just for good measure, we only estimate that our findings about this are just kind of okay. We want to keep ourselves in check a little bit too, right? Take our own medicine. How are we doing on time? Got a little bit of time. So, I'll tell you what, I'm going to skip through a little bit of the next 3 slides, but I'll give you the take-home message is basically we, instead of looking at that stimulus response sort of framework, we found in our oscillations of brain activity that if this is stimulus, we found theta activity actually reliably differed for successful memory before the stimulus showed up on the screen, and that reliably predicted memory behavior. That was an accident during my dissertation. Also why it took me 5 years to test 3 people, because we were doing a bunch of other studies. And that led to some postdoctoral work where we looked at some of the brain structures involved. We used fMRI, and we found that we actually discovered cortical effects for that too, as opposed to just the neurophysiology of the scalp. We found it both in the cortex and in the hippocampus. But what was interesting about this, it was actually negatively predictive. And what you see positive, this is predictive to false alarms, which is false memory. So it turns out your pre-stimulus brain states can predict good and bad memory, which should not be super surprising, because think of it kind of like your brain's mood. You're in a good mood, you might do well. If you can also be in a bad mood and maybe not do so hot. We found that it predicted both if and how people remembered, and there are evidence in the cortex and hippocampus that can be both helpful and hurtful, perhaps reflecting sort of pattern completion through an optimized networks. And that led us to be able to manipulate memory through this audio-visual device that actually, if people received theta frequency, which is what that was, we said, if our findings are true, we should be able to manipulate it and improve performance. And indeed, that's what we found. When we gave that theta frequency, we measured it being entrained with this audio-visual stimulation at these frontal sites, and that difference is the improvement due to that intervention, which gives us a lot of ideas of where we might take that future, both clinically but normatively, and also in some applications for countermeasures and some of the spaceflight stuff I'll talk about in a minute. So that's kind of where we are there. Pivoting. Is it okay if I pivot? Do we need a breath, fresh air? Okay. So this is usually when I practice this talk before I gave it to students in my class, and they said, it was okay, they said, but you got to have a lot less psychology and more space. And so I kind of switching to that now, and I want to try to form that connection of where these two worlds connect, without a pun intended. So we need optimal brain states for cognitive performance, right? So NASA recognizes that, and that's kind of that bridge from the brain states that we were working on discovering in the laboratory. If any of you guys remember the movie Interstellar, this is basically a fight between 2 heartthrobs, Matt Damon and Matthew McConaughey. They're about to have a battle royale, and somebody's about to die, it turns out, in the movie, because they can't manage the team conflicts. They can't manage the psychological stressors of being isolated and confined. And this is what we want to avoid, right? And psychology, neuroscience, and our teamwork dynamics studies are really going to be key here. which kind of cross-pollinates between neuroscience, psychology, and IO psych. So the way that NASA is looking at that is what's called the Human Exploration Research Analog, short for HERA. So it's an Earth-based facility at NASA Johnson Space Center where they study, it's basically NASA's largest psychology study because every 4 months they cycle a new crew through for many, many years now. This is part of our habitat. I'll give you a little bit of tour of that later. I had the privilege of being a crew member for that and the dubious distinction of being the only professional psychologist to have ever been a crew member on NASA's largest psychology study. It was an accident. They didn't want me. They called me and said, you got the best resume we've seen for this mission, but we want to call you, let you know, thanks, but you're permanently banned. You'll never do this for us. I said, okay, thanks, but why? And they said, well, we're studying psychology, learning, memory, all these other processes. It happens to be what you do. We think you're not going to be a naive test subject, and you might know a little bit too much about it. They were right. I said, ma'am, you might have a misunderstanding, though. I'm not nearly half as smart as my resume seems. You can ask any of my friends, and they must have. And she said, well, we need backups a lot, and so we'll keep you on. And I ended up getting asked to go as a backup on about 3 days mission, 3 days notice for the mission, and the rest, as they say, is history. So this is our crew, and we're basically, it's a laboratory that's specialized for testing human systems for deep space travel. It's on the ground in NASA Johnson Space Center. It's a 45-day mission. And we're kind of like the test pilots of the human mind. We test lots of stuff, group dynamics, teamwork, nutrition. It's a sleep deprivation study, so chronic sleep debt. And then they test your psychology and your neuroscience and how you get along with people when none of you guys are sleeping for 45 days. And you still can't leave that camper with 4 of your coworkers. So.
Twins.
What's that?
Use twins.
Use twins. Yeah, well, they might need some fresh air too. So anyways, that's kind of what we're doing here. Again, 45-day mission, and the idea is that our capsule would be one of these on a long-duration flight, and we live in that, and it looks like this at NASA Johnson Space Center. There's 3 stories. This is our sort of vertical column. On the back over here is basically the bathroom and the shower, and that was our home away from home for quite some time. During most of the time, we did a ton of psychological surveys, teamwork studies, team cohesion questionnaires on everything that was going right and everything that was going wrong. People always ask, what were the manipulations? What did they do to stress you guys to make things go wrong? And I always say, nothing. Just let people be. It'll happen. And it does. And we work it out. So a lot of surveys. But besides the psychological side, we're also looking at the neuroscience. And so one of these things is like the SpaceX Dragon. I think these launch not too far from here, right? And they resupply the vessels. And we wanted to measure the psychology and particularly the neuroscience of those cognitive errors. So cognitive errors of attention can be really important. You need to use the Canadarm to grab that resupply vessel full of your food. Or maybe just notes of loved ones from home, brighten your day for the next 3 months. This is what it looked like on our simulators. That's that delivery vehicle. This is the arm trying to get it. And you've got to sink that pin inside this kind of target. And you've got all these different degrees of freedom in your joysticks and controls. And you've got to get this thing in there. And you haven't slept for a long, long time. Your teammates might be bothering you. You're stressed. You're doing a bunch of other stuff on the mission. It's very much like spaceflight. And this is what that simulator is going to do, and we want to look at the brain activity of it. This is me actually doing that. We have a controller here and another controller here to calculate the different dimensions of movement that you have to control. And this is something called functional near-infrared spectroscopy. So we're capturing blood flow in the frontal cortex as well as some EEG around there too. Not just to capture the successes, but particularly to understand what's going wrong when we have misses and we fail on capturing our food supply vehicle. So that's what's happening up here. We did a lot of neuroscience in there too. This is more functional infrared spectroscopy and EEG. This is me in the MRI scanner. Ever the neuroscience nerd, I would not do that without my Mars socks on, which are there. I think I'm wearing them today as well. But I was really excited because I was the only neuroscientist and psychologist to do this study. And to me, it was very gratifying to get to do that opportunity because I had indeed started as an undergrad doing that. So that's me. here and here, as probably 19-year-old learning how to do EEG, and almost 20 years later, getting to do it in a NASA flight suit for a simulated mission to Mars is pretty special. And so it really made me appreciate the training I got as an undergraduate and underscore the motivation and passion to return that and pay that forward to others. And so that's what we do in the lab where I'm at right now, Cal State San Bernardino. This is Alana, whose work I showed you earlier, and this is Lindsay. Lindsay's now actually, she was a master's student who's now graduated and now actually is returning and works at NASA Johnson Space Center at the Behavioral Health and Performance Lab, running that laboratory, now scoring some of those psychological interactions of the teams in HERA. So it's really gratifying to see that circle connected and to pay that forward. And these are a team of our different laboratory students as well as students in different research classes we teach. And we've been able to take that forward now and actually bring that back to Florida. So I'll finish off by talking about this last mission we just completed a few months ago, I should say this past summer. It's called the NASA Extreme Environment Mission Operations. So just shorten that for NEEMO. It's the only place on Earth to study the closest thing to space. So astronauts live in a tiny capsule, this capsule, actually, underwater for about 2 weeks, about 100 feet down. And they escape every day if they want to go do about a 4 to 5 hour dive operation under saturation diving conditions, which is basically your extravehicular activity, or what you might call a spacewalk in space. So it's very, very comparable to what you would see in space, at least insofar as we can on Earth. And it's a great way to give a platform to study cognition. Now, this happens in the Florida Keys at a station run by FIU in Isla Mirada. If any of you guys go down there and fish, you might know that spot. But we had an opportunity then to take our research there and to get our students involved and to pay that forward from what I got to see as a crew member and now work as a PI with a large team of many big different institutions. So it's a huge team effort, very complex operation. It took us about 1.5 years to really plan this through and work this through. It's incredibly challenging, to be frank. Our team was a collaboration with a colleague at UC Riverside, Dr. Weiwei Zhang, and our project was led by Alana Muller and supported by Constance Greenwood and Rachel Marino, who are 2 undergrads who are now in charge of running the lab back home. And what we did was a simple task of psychomotor control. So what it was is people had to grip, a hand grip like this, at either 20% or 45% based on the scale. And then they had to perform a flanker task, which is a way to study attention and distraction under cognitive load. We had to really simplify this from the way that we would do it in a normal laboratory. This is kind of the big idea. It's a way to measure short-term attention, and we wanted to do that after an EVA to assess the impact of that exhaustion, the workload, on these core cognitive measures, so that we could not just characterize it, but then develop countermeasures like entrainment or brain stimulation at TDCS, so that we can improve this in support of those sort of NASA grant calls to improve these cognitive deficits in spaceflight that could potentially be so catastrophic. So our task, as I said, you're going to hold and squeeze this grip up to a certain level that's easy or another level that's harder, and then you're going to be asked to pay attention in the middle and to press a key based on whether it's a Z or an X. Your performance is less important than your speed. We're going to measure reaction time to see that impairments, that sort of flanker compatibility effect. And we hope that it will enable future spaceflight objectives by being able to develop these countermeasures to mitigate deficits that we can characterize. And the basic plan is that we did that every day in the mission. We call it Mission Day 1, Mission Day 2. So MD, they'd go out and dive, they'd come back and they'd test. In the future, we hope to have some projects up and running again in the summer. We'll bring students there as well where we record brain activity and do these interventions. This study was a behavioral one to characterize those deficits. And we do the mission, but we also proceeded by baseline testing at Johnson Space Center, which was a real treat because we got to bring our students down there and let them share in the excitement and actually have a really fantastic career development opportunity. We took them to Johnson Space Center. This is sort of a booster of one of the Geminis. This is the Apollo 11 guys. The girls thought it'd be fun to replicate their stance and their image. And then we got the Redstone rocket in back there. And they got to work with the astronauts, including Jessica Watkins, who's a NASA astronaut. And here she is on the right-hand side doing her task. And that was our broad team there with our other 2 aquanauts, 2 of whom were actually scientists from Florida, at USF and Harbor Branch as well as here. So Shirley DeAugustino is a marine biologist at FAU Harbor Branch, and Chilla is at USF. It was a special day for them because they worked about a year to really optimize this task and design. And then I backed off, and I let them run with it. And it was special for them, particularly because they had, I think it was the first all-female NEEMO crew, and they were tested by essentially all-female scientist crew. And the girls find that really pretty gratifying. One of the astronauts was Samantha Cristoforetti, who's Italian from ESA. Apparently she has her own Barbie doll too. And the girls got to meet with them, network with them, get to meet them and talk with them. And I think this is actually at Jessica's 30th birthday party. So they got to have some beers and do that. So that's kind of that. And the last parts here are just kind of some pictures. I know it runs short on time, so I'll wrap it up. These are them actually getting to see the inside of the HERA capsule and sort of the spacecrafts of the future as well as those of spacecraft past. This is the Saturn V. Some of you guys might recognize that from out here at Kennedy. They found that was certainly very special. Got to bring them inside this, space shuttle cockpit, which is pretty cool. So here's Alana taking a selfie from there, which is kind of fun. We came back. She pretty much won every award the university had to offer, from our president, our provost. Reported back on some of her findings, and then we actually returned to Florida and ran the mission. So these are the aquanauts and the astronauts underwater working together in these team dynamics. This is Alana, and we're here in mission control where we watch them do our task. This is their crazy timeline of their workload of everything they have to do. That's essentially what we're doing, running that mission while they're doing their work about 100 feet down. And then they can either do an underwater waterproof iPad or these cognitive tasks in the capsule. Briefly, our preliminary data, what we found, we did see some impairments. This is baseline testing. This is in the mission. This is your motor control. So you got much weaker by virtue of being in the mission. And this is that flanker compatibility effect showing differences in your reaction time, both pre and post. So they're basic findings right now. We have actually a lot of covariates. We want to still work out on that. But we're pretty excited to continue exploring that. Continued with new studies that we did on Catalina Island, looking at an exosuit. And the purpose here is to have a complete dry suit. And we're going to what we'd like to do is take mobile EEG like this, without any extra wires. It's all Bluetooth and wireless, and put this inside this dry suit so that we can actually characterize neurofeedback to serve as a way to develop these countermeasures as well for spaceflight. So you can actually take this, put it in the helmet. This is an exosuit that will go down about 1,000 feet, but we want to use that as a platform for actually integrating, not just in the space helmet for astronauts up in space, but we can use that for working with clinical patients as neurofeedback. We can work that for developing that for market-based purposes, for video games, or anything else you might want to improve cognition on. We're kind of excited about these future directions, really moving to this more mobile designs, working towards developing countermeasures, things like entrainment, things like TDCS, and continuing through other studies with clinical patients that we're working on and exploring these future analog works. So that's kind of where we hope to go in the future. As you can see, it's a really good platform from which to do pretty high-octane science while giving the reins to undergraduates and graduate students to really thrive on it in themselves and to build their careers. So we're excited about that. We try to take these lessons that we learned from Earth back to live in the laboratory, which for time I won't go over now entirely, but the idea, that's Iceland we learned as a crew, we try to take back as a PI, not to the lab, is see everything as opportunities, not as obligations, and find peace and it'll bring you joy, bring others joy and it will bring you peace. And if we can do all that a little bit more on Earth, we might never want to leave it. So a note on teamwork there as we all seek to work together. And thank everyone on the teams that have certainly participated in this. Would not be possible without the undergraduate and graduate students, but also the mentors who supported me when I was an undergraduate and graduate student as well. Certainly the crew teams as well, our families and the funding programs at the NIH and and the institutions that have supported us are very grateful for. So I probably went over time a little bit, but I appreciate your guys' patience, and maybe we can talk about questions offline if you guys have other things to do. Thank you.
Thank you. I think some people have to get another meeting that's going on in that too.
Thank you.
How long was this?